Number 9 is a question from Unit 7 where we are given a sequence 1, 3, 3 squared, and 3 cubed. And that function is going to continue on infinitely because we see those dots that follow the first 4 terms of the sequence. The question's asking how many terms must be added together for the sum to equal 3,280. This is an example of a partial sum question. In a partial sum, formula can be generated, but we need to determine if this is arithmetic or geometric first. So from 1 to 3, 3 to 3 squared, or 9, we're multiplying by 3. 9 to 3 cubed is 27, so 9 times 3 is 27. So that means our common ratio, r, is equal to 3. So the partial sum for a geometric sequence, that formula is on your formula sheet. It looks something like this. S sub n is equal to the first term multiplied by 1 minus the common ratio to the n, the number of terms that we are summing up, divided by 1 minus r. So let's plug in all the information that we know for this sequence. We know the partial sum is 3,280. We know the first term is just 1, and the common ratio is 3. It's that n, the number of terms that we aren't sure about. Then all we need to do is solve for the variable up in the exponent. So what we're going to do is multiply both sides by that denominator, 1 minus 3, or negative 2. When I multiply both sides by negative 2, the left side of my equation is negative 6,560. This one out front can just go away since it's just a nice little constant value. And now we need to isolate the base of this exponential. So subtract 1, negative 6,561 is equal to negative 3 to the n. Divide both sides by negative 1. Now we're dealing with a positive. 6,561 is equal to 3 to the n. At this point, you could guess and check to figure out what that exponent needs to be, or you could convert it to a logarithm. Log base answer equals power, so log base 3 of 6,561 will equal n. I can evaluate this on the calculator by going to my nice log base function. I hit math. There it is, letter A, log base 3 of 6,561. The value of n is 8, so we need to add up 8 terms to get a sum of 3,280, that original problem. Number 10 gives us the first term of an infinite geometric sequence. That's nicely underlined for you now because you should be queuing into something that we talked about in Unit 7. An infinite geometric sequence has a sum as long as a few rules are intact. It says the sum of the sequence is 6, and we're trying to find the common ratio. So we have to work backwards here. The sum of an infinite geometric sequence is equal to the first term divided by 1 minus the common ratio. If the sum is 6 and the first term is 2, all we need to solve for is that missing variable r. As we talked about before in trig, if the variable's down low, switch, So 1 minus r is equal to 2 over 6, or 1/3 if we reduce that. Subtract 1 over, we get negative 2/3 when we find a common denominator, and then divide by a negative. The common ratio here is 2/3. Number 11, which is true of the series shown below? Well, first of all, a series is just a sum of a sequence, and that's why we have those plus signs in between each of the terms. It's infinite since we have those dots that are following the terms that are shown. Then we need to figure out if this sequence converges or diverges, since that's the language that our choices are giving us. Well, if a sequence is arithmetic, we know it automatically diverges. But if it's geometric, it could converge or diverge. So let's take a look. From pi to 3 pi over 4, from 3 pi over 4 to 9 pi over 16, we are multiplying by 3/4. So our common ratio is 3/4. We can determine if a infinite geometric series converges if, first of all, it's infinite, which we've got. Second of all, it's geometric, also just proved to be true. And the third thing, the absolute value of r has to be less than 1, which we also have true. So we get to use that same formula we used on the previous problem. The sum is equal to the first term, which is pi, divided by 1 minus the common ratio, 3/4. A series will converge to the sum. 1 minus 3/4 is 1/4. When we multiply by the reciprocal, we get 4 pi. So this series converges to 4 pi.